Okay, so let me just summarize because I'm sure you guys were, or I'm not sure you guys were like very focused on the bipolar stuff given the quiz was coming up. So I'll do a summary of the bipolar um, transistor real quick here.
Yeah, thank you.
So let's see. So what we said was that we wanted to get a gain or amplification. Fire or gain. And the first thing we said that if you had something called, so the sort of the way the story we were building the story was, if you had something called a voltage controlled current source, you get gain from it, a gain function. And then we showed that this thing called the bipolar transistor could act as a voltage controlled current source. So the voltage controlled current source, okay, so this concept is a 3-terminal device. So this here, which is the reference, is one of the terminals. Then you have this input, and then you have an output. And there's a current source on the output, and that has a basically a function of Vn. Okay, and then we said if you put an external resistor across this, so this is the voltage control current source. Okay, and then this is an external resistor, sort of the RL, and this point is V out. And we said if you had such a thing, if we just do a simple KCL here, we would get V out is minus I R sub L, and plugging in for I would end up minus K R sub L V in. So if we define something called gain, which, in short, this is a common way to put it, is A sub V means amplification in the voltage domain, I guess is what you would look at it. If we define it as V, the ratio of V out over Vn, that ends up being, so V out is minus KR V in, and V in is just Vn. So this ends up just being minus K R sub L. And if this K times R sub L is greater than 1, then you get amplification. So basically, if you get something like, bad drawing. If you get something like, in time, volts, if this is your input, say some kind of a sine wave, your output would look, it'll be an inverted version of this, but it'll be a gained up version. So the inversion comes from this sign, and you'll find out, almost all the amplifiers I know, as far as single stage amplifiers, they are inverting amplifiers. Okay, so but we said that's not going to bother us. We're not going to get stuck on the concept that the output is inverted or negative. It's just that it's gaining up the input. Okay, so that was, if we had this voltage controlled current source, we could get amplification. And then we said there's this thing called a bipolar transistor. And the schematic looks like this. It's this we call the base. This we call the collector. And this we call the emitter. And if I draw this is a sort of a cartoon of what this piece of semiconductor looks like, but it's just to give you guys an idea. The idea is that this device is a sandwich of two polarities. It could either have two ends and then a P in the middle, or, so this would be called an NPN. Most of the time in the class, we'll be talking about this. And this is the device that's mostly used. And it has a higher performance, but you could easily get, I'm just going to draw it really small here, but you could also get a bipolar transistor that would be PNP. Okay, and that was called a PNP. We'll get to that at the very end of this chapter. But basically, it kind of looks like everything is similar to the NPN as far as the analysis, except all the voltages are the opposite. So anyway, as long as you have this NPN structure, you have an NPN bipolar transistor. And this is the schematic for it, schematic symbol. And if I was going to draw these same terminals, this would be called the emitter. This would be called the base. And I didn't give myself a whole lot of room here, but just move these guys over. Whoops, that didn't help. This is called the collector. And we said that if you connected up this bipolar transistor in a bias condition, remember bias condition and the small signal analysis. We'll get to the same concepts in the transistors, but remember the diodes. The bias condition is when you put the voltages on the device to put it in a particular state that you want it to operate in. So if we were going to bias this thing up in the condition called forward active bias, or active bias or forward bias, what we would do is we would take the bipolar transistor, we would put a voltage on the base such that the base emitter voltage, so I'm just going to call it VBE, and I'm just going to call it 800 millivolts. But basically what we want to do is make the base emitter voltage make the base emitter junction forward bias. Okay, remember this just looks this part. So here, so we're making this P greater than this N. P is bigger than N. So it just looks this, if you just look at these two, or this junction here, it just looks like a forward bias PN junction if I put 800 millivolts on it. Okay, so that's step one. Yeah, go ahead.
So that would be like having a diode with VD on, right?
Yes.
Pretty much?
Yep, that's correct.
Thank you.
So that you're making this junction forward bias, and then we're going to make this junction between the base and the collector reverse bias. Okay, so basically we're going to make, we would put, say we want to make the collector, for example, you could make it higher than this, but let's say if we make the collector base voltage, so excuse me, sorry guys, but there's a bunch of like voltages running around here, but so pay attention to these VBE. So that's the base emitter voltage. Now I'm drawing the collector base junction, so the voltage difference between the collector and base. And I'm going to make that a little reverse bias. Just give it 200 millivolts. But because, like, let's say in the lab, if you have a excuse me, guys, if you have a voltage source, you'll be connecting it to the ground. What you'll really be connecting to this guy is a voltage like this to the ground. So it look like a collector emitter voltage. And if I make that, like, say 1 volt, because I get 800 millivolts at the base compared to the emitter, if I make this 1 volt, it'll make this junction, the base collector junction, reverse bias. It'll put 200 millivolts across that in a reverse bias way. Okay, but usually you put, you're not, almost always, you don't put like a, a voltage source between the base and the collector. You put one between the collector and the ground, or where the emitter is. Okay, so if we do that, what we said was, what this does is and then, sorry, there was a couple of other things, a couple of other conditions. So if we put that in, and if this NPN transistor is correctly designed as a piece of semiconductor, and that means that we dope this emitter very heavily. So this is donor doped, and this is acceptor doped. So if the number of donors here, the density is much higher than the number of acceptors, what happens is, if this node, if the base emitter junction is forward bias, then because there's a whole lot of electrons here and not too many electrons here, you'll get a bunch of electrons from here just from diffusion going over. So what happens is you will get a bunch of electrons going to the base from the emitter. By the same token, you're going to get a bunch of holes. So sorry, this is electrons. So these are electrons going from the emitter to the base. And then you'll get holes because there are more holes in the base than there are in the emitter. You're going to get holes going into the emitter. But because the doping concentration of the, and we'll see the equations later on today, I think, because the base acceptor concentration is much smaller than the emitter donor concentration, the current of the holes is going to be a lot less than the current from the electron. So you're going to just get a lot less holes than you do electron, just because of the difference in the doping concentration.
And this is in forward bias, correct?
That's in forward bias. So basically, this guy, this junction is forward bias, and you're just going to get electrons are going to diffuse across, and holes are going to diffuse across. And then the other thing, so basically you get this mismatch, which is something you need for the proper operation of the device, between the number of electrons and the number of holes. So the first thing you do, first important thing, is you've got very high doping on the emitter. And then the second thing you got to do in the design of this piece of semiconductor is to make the physical width of this base, I'm going to call that WB, width of base. You want to make it short. And this is also very important to the operation of the device. So what that means is, if it's if this is very, very narrow, if WB is very, very short, if this distance is very, very short, these electrons will just go through the base, and they're going to hit this junction, which is reverse bias, because we made it reverse bias. So if this junction is reverse bias, if it sees electrons, it'll have a electric field. Because it's reverse bias, it'll have an electric field from here to here. Okay. And basically, as soon as that electric field sees these electrons, if it's short enough, all these electrons will get to here. The electric field will push these electrons into the N side. So what you'll end up having is a current of electrons going from the emitter through the base to the collector.
Professor, I know this is. Oh, go ahead.
Oh, sorry. So you said this is reverse bias?
So the collector base junction is reverse bias.
Because the last lecture, the last thing that you touched on this, you said that this was actually forward bias.
So the base emitter junction is forward bias.
Oh, okay. So, yeah.
I apologize if I screwed that up, but basically in this op mode, the base, there's two junctions, right? Because we have N, P, N. So there's a base emitter junction and a base collector junction. The base emitter junction, you'd like it to be forward biased. So you put you want to make this P more positive in voltage than the N by more than a VD on. So that's why I put this 800 millivolts there. And then you want to make the base collector junction, you want to make that reverse bias, okay, by some amount. So I put this collector emitter voltage to give it about a 200 millivolt reverse bias. I could have put 3 volts here and made it even more reverse bias. It's not very important. Did that make sense, Absalon?
Yes, thank you.
Okay.
So are you modifying this thing to give yourself either a forward or reverse bias by changing the width of the base or doping one side or the other more? Is that what I'm getting?
So let's see. Let me see, how should I explain this? This is confusing. Let me.
Don't you make it by making? Give me a second.
Professor, I read that the positive section of the transistor has to be slightly doped. Why is so?
Okay, let me sort of answer all of these at the same time. But thanks, Manuel. Let me give you 1 second. Any other questions about this?
Thank you, Professor.
Yeah, sure. Any other questions about this? Let me start from the beginning. I think I was like confusing you guys. So let's say when you guys go, you can go and like buy a bipolar transistor. And you can use it in the lab. Okay, so this would be like a discrete, it has like 3 pins, 1 for the collector, 1 for the base, 1 for the emitter. So it comes pre-built from whoever is the company selling it to you. Man, my handwriting is really bad. Bipolar transistor. So now you've gone and bought this thing. Okay, and so this thing, what the designers of this device have done to make it a good bipolar transistor, so you'll want to buy it, is they have made this emitter N+, they have made this base much less doping concentration than the N+, so in terms of the number of acceptors. And then this N is usually sort of along the line of the base or even less. Okay. So William, does that make sense? So it comes pre-designed in that way. So you as the user of this bipolar transistor are not adjusting doping concentration. This comes to you as a device that you buy or you use.
Okay, so when you talk about width or doping one side or the other, that's just a behavior of like current direction, forward or reverse bias, or?
Yeah, that's correct. But
okay.
to get a good transistor, it needs to be like this. And the reason I'm mentioning those is because when it comes to explaining why it does what it does, they're important factors. Okay, so it comes designed with a high doping concentration on the emitter, and it comes designed with a very narrow base width. Okay, so so this is the point of a transistor. Okay, so let's talk about this now. What you want to do with a transistor is you want a three-terminal device. So I think this is pretty generic. So let's say if I call a transistor and I want it to be a black box, you want to have one terminal that's the control terminal, and it's either control voltage or a control or current. Okay, and basically you want that to control the current from across these other two terminals. So either you have an I in or VN.
And that one would be the base, right?
That would be the base. Yep.
Okay.
And then you have an I out between the other two terminals, which would be the emitter and the collector. So what you want is you want like imagine if you had a switch, right? Your light switch in your wall. So if you had a switch, we're not talking about switches quite yet. You could use bipolar transistors, any transistor switch. That's one of the functions. Is you want a control thing, which would be where your finger goes. I don't know what that's called, but it basically throws a connection between. So this is inside your walls between between X and Y, but this guy's the control. Does that make sense, William? That's a really badly drawn switch. So you've got a light switch. You're basically saying, connect those 2 points, turn on the light, or disconnect them to turn off the light. Okay.
So applying the control voltage or current will allow current to pass or not allow current to pass
across these other terminals. So when you're using the light switch analogy, the current doesn't go into your finger; it's just going through the switch to your light bulb, right? That switch that your finger is controlling is either turning off that current or turning on the current.
Okay, so it's like a mini, actuator. What are they using?
Yeah, I mean, but I'm sort of trying to don't overthink this analogy. Hopefully I'm not going to make you more confused, but I'm trying to give you a vision of a three-terminal device. So that's a three-terminal device. You have one terminal, which is what your finger, pushes up or down as a switch on the light bulb, or the switch on the wall, and then the other two terminals are the outputs of the switch, sort of connecting your light bulb to the power or not. Okay. And then what you'd like to do ideally is you'd like to make the switch where your finger is on, you might want to make that easy to switch. If that was such a painful thing to move up or down, it wouldn't make a very good switch. So by analogy, what you'd like to do is to have a very small, you want this input current or input voltage, let's say the input current, to be a small quantity controlling a potentially large quantity.
Okay, so just so I'm clear, it's that control voltage that's deciding whether this thing is forward or reverse bias between X and Y. That's what's happening?
Yeah.
Okay.
That's correct. And you want, when you're forward biasing it, when it's on, you don't want to be pumping a whole lot of current in here. So because this current coming from the base to the emitter, when you're forward biasing this node, remember there was a current that comes, there's a current from the emitter that's diffusing out to the base in electrons, and that's going out to the collector. But then you have a current coming from the base to the emitter because this junction is forward biased. We made it forward bias, but then the base has to supply this current. And we want this current that the base has, your input has to supply, we want to make that as small as possible compared to this current that's going to the output. Okay, because we don't want to load down the input. So that's why we make the emitter much higher dope than the base, because that way, one way to look at it is a small current from the output, from the input, sorry, a small current going into the input controls a large current going through the output. If that makes sense.
Yeah, that makes sense. Thank you.
Because I mean, think about it. Imagine if this emitter current, this is the current on the output, you wanted to make that a milliamp. If the P and the N were the same doping concentrations, you'd have to shove a milliamp into the base to get a milliamp out. But that would really load down whatever is driving our bipolar transistor the previous stage. So what you want to do is to have, say, I don't know, like 100 microamps or 10 microamps controlling 1 milliamp. And that's why you have such a big disparity between the doping concentrations. Okay. Did that make sense, guys? Did that clarify why you would have the emitter be highly doped? Is because you want to have a small current controlling a large current.
Yeah, it does make sense.
That makes sense? Okay. So basically this device comes to you made.
So Professor, it's like having a voltage controlled current source?
Exactly, that's what you want, a voltage controlled current source. Exactly.
Okay, cool.
But you guys will see as we build this, as we describe the bipolar transistor more and more in this lecture and the next one, why these various things are important. These things that I'm saying about, you want to make the current small going into the input, etc. But in the end, you want a voltage controlled current source. So you basically buy this device pre-made, and what they've done again is to make this emitter highly doped and the base very narrow. And then what you do is, what you have control over is you buy that device. Now when you have it in your hand, you think of it sort of in a schematic type mode. You no longer are necessarily thinking in terms of NPN and doping concentrations. What you know is you'll have to make, to get good gain out of this, you'd have to put a voltage here to make this guy forward bias. And you need to put a voltage here to make this guy reverse bias. So this is what you have control over as VBE and VCE. Okay, and if you do that properly, if you make the base emitter voltage forward bias and the base collector voltage reverse bias, what you'll get is this device acting as a voltage controlled current source. With this being the emitter, this being the collector, this being the base, and this current being, this collector current being, let's see, it'd be I sub S exponential of VBE over VT. So this would be VBE. Okay, so basically you get a voltage controlled current source that's got an exponential relationship between the input and the output. So a small change, a very, very, because it's an exponential. If you have a tiny little bit of, once it's biased, it's exponential. A little change in the VBE, a small change in the VBE will give you a very big change in the current, collector current. Okay, and then if you have, you connect a resistor across this, you get a gain basically for that current going there. Everybody with me?
Yes.
Yes.
So I'll just keep hitting you guys with this thing. It'll, unfortunately, it'll beat this horse to death.
Good, because it's starting making sense now.
Okay, good. But no real horse was harmed during the making of this bipolar transistor. But okay, so here we go. So where we are is that we have this bipolar transistor. So this is so up to this point. To this point, we know we have a bipolar transistor, and if we put it in this forward active mode, if in forward active bias condition, we get, so we'll get large electron current from emitter to the base to the collector. And we'll have a small current, small hole current from the base to the emitter. So this is like the output current. Is a large electron current, and the input current going into the base is a small hole current. Okay, so we know this so far. Okay, so the next step for us is we're going to look at a few questions here, okay? So one is, how do electrons go across the base? Is it through drift? We only have two options. Is it drift or is it diffusion? Because I just said they go across the base, but how does it work? Second question is, how does collector current depend on terminal So here, I just claimed that the collector current is an exponential relationship on the base emitter voltage and no relationship to the collector voltage. So I just gave you guys this equation, I sub s exponential VBU VT, but I didn't prove it to you guys. So that's this step B is what we're going to look at. And then the C, which is the third thing we're going to look at, is I said the base current is small, but how large is the base current? So basically, we're trying to answer these three questions And once we do that, we'll have a sort of a complete equations between the three currents. So we have three currents. We have the emitter current, we have the collector current, we have the base current, and then we have the voltages on the three terminals. The voltage on the emitter, voltage on the base, voltage on the collector. So once we answer all these things, that's what we'll see. Okay, so the first question, which is so if you look at this question is, how do the electrons go across the base? That's a pretty simple answer because, so this is basically, if you look at, this is the N plus of the emitter. This is the N of the collector. And this is the P of the base. Okay, so the question is, these electrons that go here, how do they get from here to get swept away? We know they come from the emitter to the base by diffusion. We know they go from the base to the collector by drift, because there's an electric field there because it's reverse bias. But how do they get across the base? And that's, the answer is that the base is, base is doped. Although it's doped less than the emitter, is still doped with acceptors. So it's a moderate, the book calls it a moderate conductor. Means a pretty good conductor, and it means that the base can't support an electric field. So if you put a voltage sort of here on the base, you won't get a difference between these 2 points because you get very good conduction between these. So you don't get a voltage difference across the base. So this means that there's no E field across the base itself. So no drift current. And the upshot is, this means electrons diffuse across the base. Okay, so we're saying these electrons are coming from here to the collector somehow. We can't create an electric field across the base because it's the doping concentration, although it's lower than the emitter, is still high enough that you can't put a voltage, you can't support a voltage there because the resistance between the 2 points is low. It means there's no electric field there, so which means that the electron just have to diffuse across the base and get to the collector. Okay. So what does that mean? Let's draw this. I'm just going to draw this sideways. I think it'll make a little bit more sense sideways. So draw. This guy is, so this is N plus, so this is the emitter. This is P, which is the base. And this is the N, which is the collector. Okay, and then we've grounded the emitter. We're putting a VBE across the base. And then we're putting a DC across, so let's say 1 volt or something, across the collector base, across the collector and emitter. And so we have, so let's see. So Again, this, what should I draw it with? So this guy is, it's going to get crowded a second. So anyway, so this guy's forward bias, this guy's reverse bias. So then let me superimpose a couple of axes on here. So this axis is distance. Okay, and let's call this point x1. This is the base emitter junction location. And let's call x2 the base collector junction. Okay, so we said that because this base emitter junction is forward bias, we'll get electrons that diffuse from the emitter into the base. So if I was gonna just draw, so I'm gonna make this axis carrier concentration. Or the change in carrier concentration, maybe is better to say. So here, compared to what it was before it was forward bias, we get a bunch of electrons that just enter this side of the base over here. So if I look at the carrier concentration just there, it looks like I have a bunch of electrons. Okay, and then by the same token, if I look at this side, the emitter side of the base emitter junction, it looks like I have more holes than I had before. A bunch just diffused across, but so I'll have more holes. Whoops, but not as much. So the number of these holes is a lot smaller than the number of electrons. We already talked about why, because this guy and the emitter is doped much higher than the base. Okay, so that's on here. And then if you look at what's happening in this side of the junction here, in terms of the electrons, so basically the base collector junction, we said that all the extra electrons here get swept into the collector. As soon as they hit this point, they're going to get swept into the collector. So here there won't be any extra electrons. So there'll be very few electrons here on this side. Okay. So basically the way the electron concentration looks across the base is something like this. Okay, it's very high on this side, on the emitter side of the base, and very low on the collector side of the base. Okay, so we have this gradient, this change in the carrier concentration from x1 to x2. From x1 to x2, you have this change in carrier concentration, this electron concentration.
Is this like a efficiency loss or?
No, because I mean, all of these things are gonna basically you're sort of creating a current that's going this way, but they're just getting swept away. Okay, because there are few electrons here, so the electrons get pulled here. Imagine if you had again, hopefully it won't be a crazy analogy, but imagine if you had like I don't know, like a pool or a faucet, some kind of a place where you're shoving a lot of water on this side, and you got a hole on this side. So you're pouring water in this side. So you have like a bunch of water here, but it's draining away this way, and there's a gradient of water across. Maybe a bucket is a bad example, but let's say it's a stream or something. or something going into a waterfall where water's coming in here and then it's going away this way. So all these electrons are eventually getting from the emitter to the base to the collector, but they're just not hanging out here very much. As soon as they get here, they get swept out to the collector. Does that make sense?
Yeah. So it's like a small area that the electrons are being pushed through to a big area that they're exiting.
Yes. Yep.
Okay. Thank you.
Sure. And then we're going to use this change in carrier concentration to figure out what this collector current is. So now I'm going to. You guys have two choices. Well, let me write it down. But like, you don't really need to know the details. In the end, you need to know what the equation at the end says. But let me just follow me for a second. But don't get stressed out if it seems confusing. Okay. So because also I have to refer to stuff from slide deck 2. So if you go back to the PN junction slides. So PN junction class. So this was, I don't know, but it was going back to like lecture 2, lecture slide deck, slides number 2. I think it was slide 18. And we had a equation for the change in the number of electrons. So we had an equation that described what would be the change in number of electrons on this side of a PN junction if we had a voltage across the PN junction. And I'm just repeating that equation. So it was the concentration of the dopants in the emitter. So I'm calling that Ne over exponential of V0 over Vt. V0, if you guys remember, was the built-in junction potential. I think we ended up calling that Vd on. Okay, times the exponential of VBE over Vt minus 1. Okay, so basically this was the equation that described if you had a PN junction, and on the N side you have a certain doping concentration, Ne, and a certain forward bias voltage, what would be the difference in the number of electrons that would show up on the P side through diffusion across that PN junction? Okay, so that's the equation for this. So at X1, so if I was going to look at what is this value here, this change in number of electrons here, that would be described by this equation. Okay.
Professor, can I ask you a question?
Sure.
The lowercase n is holes, and then the uppercase Ne is the concentration of the emitter. Is that right?
No, actually, the N is it's actually the number of electrons. It's a change in number.
Oh, okay. Thank you.
I say here, sorry, and this is the symbol for holes, or the letter for holes. It's actually an H plus.
Oh, okay.
So this is change in electron concentration. Okay, so I have this. And then the second thing, again, referencing back to the same set of slides. So back to lecture slide 2, slide 18. Or is this slide 18? I think it was the same set of slides. We had an equation for the current density of electrons for that same junction was Q, which was the charge of an electron, D sub n, which was the diffusion constant, and the change in n, the electron concentration versus distance. Okay, so if I use that same equation here, so this is, if I look at it as a current density of electrons in the base, okay, it's going to look like Q D sub n. Okay, in x1, so from x2 to x1. Okay, we basically are looking at the current density going across here. We're saying that's Q, the charge of an electron, times the diffusion constant, times the difference between these two concentrations at x1 and x2. x1 and x2. Okay. We said at x2 here, we have, because all those excess electrons get pulled into the collector, there's no change, there's no increase in carrier concentration compared to what you normally have. All of those get pulled into the base. So we make that D sub n, so let me just write it, D sub n x2 minus D sub n x1 over the width of the base. That's the delta x. So let me actually just write it down so don't take any, minus x2 minus x1. Okay, so now this delta n x2, okay, is excess carrier concentration or electron concentration at base collector junction. Okay, we said that is 0. Okay, and then we have an equation up here for delta nx1. We have an equation up here. Okay, and then x2 minus x1, that's a physical distance, that's the width of the base. And I call that WB. Okay, so if I was going to write this thing again, so the current density of electrons across the base is QDN 0 minus delta N x1 over WB. It's the current density. So, and then if I want to say what is my current, I would multiply, so this would be, yeah, so my current would be J, the current density, times the area of the emitter. So AE is so this Jn, again, is the current density. This is the actual current. So all I have to do to get the current from the current density is multiply it by the area over which it's flowing. So this would be this this is drawn as a two-dimensional drawing, but it's really three-dimensional. So it's the area of this base emitter junction, which is the emitter area, so-called. Everybody with me so far? Okay, so then, yes. Okay, great. So I'm going to just put in, so this is the collector current. Remember, this is the current that's going across the base. okay, is equal to, I'm gonna plug in, well, just I guess I'll plug in everything. So I'm going to say this is Q D sub n, A sub E, here I want to get rid of this. I want to get rid of this negative thing. Okay, so I'm going to basically change. I want to use this equation that we had, which is, I'll just write it here, which is that exponential of V0 over Vt. So I want to get rid of this guy. Okay. Again, this is going back to this slide 18 from lecture 2. That value was Ne, so the emitter concentration, doping concentration, base doping concentration over Ni squared. Okay, so I'm going to substitute that in here. And get Ni squared over WB n sub B exponential of over Vt minus 1. Okay. Then I'm going to call something called IS. I'm going to put all this stuff into a term called I sub S. So that's equal to Q dn. Go ahead.
The variable on the on top is Ni squared.
Yeah, that was the
Ni?
yeah.
Okay.
Ni. If you guys remember,
Thank you.
was the intrinsic carrier concentration. And that was 1.08 times 10 to the 10th per centimeter cubed. So if I use this, I'll end up with I sub C is equal to I sub S exponential of VBE over VT minus 1. Okay, so that is my equation for the collector current, which I was claiming. This is this equation I gave you guys up here. And basically by making the assumption that I have a bunch of electrons here, they're diffused across from the emitter to the base, and I have 0 extra ones here because they're all gone across the base. By making those assumptions, I plug them into this current equation for diffusion current, which we had from many lectures ago, and I ended up with the equation. And so these are the things to remember. Okay, I'm just going to tell you guys, hopefully. So hopefully I won't be wrong about this. So the things to remember are, so out of this whole calculation, right? All you guys need to remember is this equation. Okay, so IC is equal to I sub S exponential VB minus 1. So remember I sub C equation.
Professor, sorry to interrupt you, but is the VB over VT only for the exponential, or is a minus 1 included in the exponential?
Thank you for bringing that up. Yep. No, you're right. I miswrote it.
Okay, I was just making sure. Thank you.
Sure. Thanks for asking. Let me clean that up. Okay, so remember the I sub C equation, and remember the following, that I sub S is proportional to area of the emitter, okay, and I sub s is proportional to 1 over the width of the base. Okay. When you guys get a bipolar transistor that you're going to use in the lab, that transistor will tell you, give you an I sub s value. Okay, it won't necessarily ask you to calculate doping concentrations and stuff like that. So when you get a spec sheet for that part that you're going to use in the lab, you can just use that I sub s value, but it's important for you to know how to use it when you apply VBE over VT. So this is the equation to remember. But then the I sub s, we'll see why it's important to know it's proportional to the area of the emitter, because that's one way to get more current if you want more current. And then the reason I mentioned this is that it's inversely proportional to the width of the base is gives you guys an idea of why you want to make the base very narrow. The narrower the base, the more current you'll get. Proportional. Okay, so that's our equation. Let's see, so let's do, so let's do a couple of examples, or at least, yeah, let's try to get at least one example. Okay, so if you do example 4.3, so it says, okay, we got a bipolar transistor. Q1 is the name of the bipolar transistor. I'm putting a certain VBE across it and a certain VCE. So let's call it VBE1, VCE1. That'll give us a certain I sub C1. And then I'll take the same transistor and I'll give it a different VBE. I'm going to call that VBE2. And then VCE2. Okay. So the question is, and then that'll give me a different IC, a different collector current, right? If we have, because the collector current is a function of VBE. So if I have different VBEs, I'll get different collector currents. So the question is, if we want IC1 to be 10 times IC2, what should we make? What should the difference be between VBE1 and VBE2? VBE1 and, okay. So basically we want to see how much we have to increase VBE1 by compared to VBE2 to get 10 times the current. Okay, so we want to basically get a ratio between IC1 and IC2 to be 10. It's the definition of the problem. So if I write the equations for each, it's I sub s for VB1 exponential VBE1 over VT. So by the way, this one, if you guys remember in the diode, as soon as we got forward bias, we could get rid of this 1. As soon as we got forward biased, we could get rid of this 1 because this exponential number was so big. So what I can say is I sub C is approximately, in this forward active mode, exponential of VBE over VT, because in forward active mode, exponential of VBE over VT is much larger than 1. So I can get rid of that 1. So I'm just going to use this part over. So it's the same transistor, so I'm going to have the same I sub s exponential, but I'm going to have a different VBE2 over VT. Okay, so I can basically knock these guys out, and then these two guys get knocked out. So what I'm going to end up with is exponential of VBE1 minus VBE2 over VT. I'm sorry, guys, I shouldn't have gotten rid of this guy. That one has to stay. Over VT is equal to 10. Okay, I just got rid of the I sub s's. So I take the natural log of both sides. So VBE1 minus VBE2 is equal to natural log of 10. And I'm going to bring the VT over to the other side. Okay, so the natural log of 10 is around 2.3x. And VT is, we know this guy from the diode equations, was 26 millivolts. So basically it ends up that VBE1 minus VBE2 is around 60 millivolts at room temperature 300 degrees Kelvin. So if we want to increase our current, our collector current, by a factor of 10, we only need to increase our VBE voltage by 60 millivolts. This is a kind of like a good number to remember for the lab, that if you want to increase your current by a factor of 10 for each 60 millivolts in VBE, that'll happen. And also it kind of tells you like how much, what a huge sort of gain you have. I mean, 60 millivolts isn't a whole lot of change in VBE, but it increases your output current by a factor of 10. So it kind of gives you an idea, yeah, this is like a good device for getting gain or getting a switch. Okay. Let's do another quick example, and then we'll end it there. So example 4.4. Okay, so now this is like I mentioned, this is the collector current is proportional to the area of the emitter, and this is what this example wants to talk about. So if you in the lab, you bought a bipolar transistor, you want to solder it onto your board and use it as an individual device, that's called a discrete bipolar transistor or discrete transistor. So that's a device in a package, and that tends to be physically big and means, it'll have a large area emitter. And it gives an example. So an area of emitter for a discrete device says that's, could be as much as 500 micrometers by 500 micrometers. So like half a millimeter by half a millimeter, say. It's a pretty big device. Then if you're designing a chip, and that's called an integrated device. So that's a whole chip with lots and lots of transistors in there. Each transistor, to make that an economic device, each transistor has to be small, which means each transistor has a small area of emitter. And it's using an example of an area of emitter of in an integrated device is much smaller. It is 0.5 micron, or that's a typical number. It's really kind of all over the place, but it's hardly ever as that big. So what it's saying is, if the question is, assume all other parameters, all other parameters the same, what's delta VBE for the same collector current? Okay, so we know for the discrete is V sub t natural log of I sub c over I sub s. Okay, and for the same thing for the integrated device. So this is the discrete, this guy is the integrated. Okay, so VB discrete, oh, sorry, VBE integrated minus VBE discrete. Over IS integrated. Okay, so it's basically a ratio between those I sub s currents. Now, we said the I sub s, I sub c through I sub s, so sorry, I sub s is proportional to area of the emitter. Okay, so all things being equal, I sub s, this is a ratio of 500 micron by 500 micron which was the area of the emitter for the discrete device, over 0.5 micron by 0.2 micron, which was the area of the emitter for the integrated device, times the I sub s of the integrated device. Okay, that would be the ratio in I sub s's. And that's a pretty big number. This ends up being 2.5 times 10 to the sixth, or 2.5 million. So I sub s this is 2.5 million times higher than I sub s int. Seems like a lot, it is. So natural log of 2.5 times 10 to the sixth. Now the thing is though, we have a natural log here, so that ends up being only 14.7. This is 26 millivolts. So this is roughly 380 millivolts. So basically the base emitter voltage for a small device or a device that's integrated into a chip needs to be 300-400 millivolts higher than the base emitter voltage for a large discrete device that you would buy. So that's what that example is showing you, is the relationship between area of the emitter and the base emitter voltage required. Okay, guys, I think I'm going to stop here. Any questions?
No, everything's good.
Okay, guys. All right. That was a lot. Hopefully it sunk in, but we'll hit a bunch of these. We'll do some more examples next time, et cetera, to get you guys used to some of these concepts. I will see you guys on Thursday. Thanks.
Professor?
Thank you.
Professor.
Yes, that's-
Professor.
Do we have any homework for this already?
I haven't put it
practice?
up. I'll put it up tomorrow for you.
Awesome.
Okay, thank you. Because the last time was a lot, so the earlier the better.
Okay,
Yep.
sounds good.
Thank you, Professor. Appreciate it.
Thank you. Have a good night.
Thanks. Bye.
Have a good night, Professor. Bye-bye.